Welcome back, grade 11s. We are exposing friction. So let's have a look now at what actually influences the frictional force. On my screen, you can see that we are dealing with both the types of friction, the static friction, as well as the kinetic friction. Now, in both cases, friction opposes motion. It is very, very important that you learn this because we're talking about it acts in the opposite direction of movement. Okay, so it is opposite to motion. When we answer questions, we need to ascertain what direction the object is moving in. So I have two pictures here on my screen. One is on a flat surface, this little one here, this box. Let's say it is moving in that direction. So that is movement or motion. What then is my frictional force? In which direction is my frictional force going to move? So is going to act. So if movement is in this direction, let's just say to the right, I'm just going to say to the right, the frictional force is going to be between the surfaces, so that's between the box and the surface that it's on, and it is going to be in the opposite direction to movement. Opposite direction to movement. Now, what about an object on a slope? So we need to be very careful when we are dealing with objects on a slope. If the object is moving up the slope, I'm going to change my pen so we can keep this constant. So if my object is moving up the slope, that's the movement going up the slope. How is friction going to work? Well, friction is going to work in the opposite direction to movement. And so friction is going to work here. It's going to work between the surface of the box and the surface of the slope. I've drawn these arrows quite big. If there's movement, obviously that arrow that's representing friction is going to be a little bit smaller because if there's an increase in velocity, then the movement has to be bigger than the force creating the movement has to be bigger than the retarding force of friction. What happens if this object is moving the other way around? So if it's moving in that direction, okay, so there's movement. If it's moving down the slope, there's still friction because the object is still on a surface. It's still on a slope. So friction is going to work in the opposite direction and it's going to work up the slope. Our second thing that we need to really get to grips with, and that is that the frictional force, both static and kinetic, is directly proportional to what? Well, to this normal force. It's directly proportional to the normal force. We get our equations from this relationship. We're going to have a look at them in a moment. But let's look at how that's going to impact our drawings and what the forces are going to look like. So over here, I've got the first example, number one, the box on the horizontal slope, the horizontal surface, there's no slope. The normal force is the one that acts up on the object. I'm going to change my color because that doesn't look like you can see it much. So this is the normal force, okay, force normal. Some of you write it with a big N. That is the surface or the earth acting on the object that is sitting on the surface or sitting on the earth. What is that equal to in magnitude? It's equal in magnitude to the gravitational force. Okay, and we know that as being ma, okay, from Newton's laws. So the force of gravity is equal to the mass times gravitational acceleration. So the mass of the object and the acceleration is 9.8 meters per second squared. We know that, right? So this is what the frictional force is related to. It is directly proportional to this normal force. So if we think about this, if we've got a light object, in other words, the mass is not big, then the force of gravity on it is going to be smaller than an object that is much heavier. It's got more mass. The normal force is going to be in the opposite direction, but it's going to have the same magnitude. If friction is about the interaction of the surfaces, and you've got an object which is being pulled down onto that surface with a greater force, obviously the frictional force is going to be bigger. So the greater the mass, the greater the frictional force. How is that related? It's related to the normal force, and the normal force is the same magnitude as the gravitational force, opposite in direction. What now about an object which is on a slope? So let's have a look at this. We have to think back to our forces and breaking them up into components. So we've got a force, whoops, that's a bit skew, of Fg. Okay, so that is our gravitational force. If we break this up into its components, we're going to have a force, let's just say it is moving down the slope. Okay, so we're going to have a force like that, which we call F parallel. It is parallel to the surface. And we have a force like that, which we call F perpendicular. Why? Because it is perpendicular to the surface and the object there. So perpendicular to the surface. What is the normal force? The normal force is the surface acting upwards, like that, isn't it? So this would be the normal force, F normal, and it is related to the components of gravitational force, the perpendicular component. It is the opposite direction, but it is the same in magnitude. That means that we can, if we put something on a slope, so it's flat on the ground, we can reduce the normal force by putting it up on a slope, can't we? Because we have then changed the effect of the normal force by putting it on a slope. If we change the normal force, we can change friction because they are directly proportional to each other. Have a look there. So the only way we can change frictional force is by changing the normal force. How can we change the normal force? We can change the normal force by placing an object on a slope. And that is why it is easier using an inclined plane to move heavy objects than to push them on the ground. So, how do we come up then with a formula that we can use? We have, for static frictional force, we have the fact that it is directly proportional to the normal force. And so we have our maximum static frictional force. Now, we don't work with the other, as the static frictional force increases, like on the graph, we don't work with those. Those get a bit complicated. So we only work with the maximum static frictional force. It is going to be directly proportional to the normal force. Directly proportional to the normal force. If we change the forces acting on the body so that we can change the normal force, then the frictional force will be changed, and that applies for both static and for kinetic friction. So we can also say that the frictional force, kinetic frictional force, is directly proportional to the normal force. We come up then with equations because we can't use the relationship for calculations. So what we can do is we can change things around and we can pop in a coefficient. It is a constant, and you've come across constants before. And the constant for kinetic friction and the constant for static friction is this symbol here. So it's a mu. It is a Greek letter. It's like a fancy U. And if we want to distinguish between static friction and kinetic friction, we put a subscript of S or we put a subscript of K. So that means the static friction and that means the kinetic friction. So it is called the coefficient, that's the word. It is mu S and it is a ratio. And a ratio doesn't have units, right? And this is the ratio. It is for static friction. It is the maximum static friction that we deal with divided by the normal force. That is the relationship, or that is now the equation, the ratio for this coefficient. So we can say mu S equals this ratio. We can rewrite this equation, and I'm going to do that in a different color so we can see it. And we can rewrite it as, let's write the static friction, maximum static friction, equals mu S, or the coefficient of static friction, times by the normal force. Okay, so there's that equation that we're going to use. For the coefficient of kinetic friction, it's the same thing. It's a U. It's that Greek U or mu, and we put a little k to tell us that it is a kinetic friction we're dealing with. It is a ratio. Here's the ratio here, so I'm going to draw it in. So mu k, or the coefficient of kinetic friction, is kinetic friction divided by, it's the ratio of the normal force. How can we write that in an equation that we can use without fractions? We're going to say kinetic friction equals the coefficient of kinetic friction times by the normal force. We have got time to quickly look at this graph and see how we can add to it. So we've already seen that the static friction is equal to the applied force. What we haven't said was that this holds true. So the static friction is equal to this, or it is smaller than. So as the static friction increases with the applied force, it is less than the maximum static friction. Over here, at this point here, where we overcome the static friction just as the object is starting to move, that is the maximum static friction. And we can see that it is equal to, then, the formula. It is related to the normal force. Remember, it's directly proportional to the normal force. As the normal force increases, so the friction is going to increase, and so we have this coefficient of static friction. What then? Well, as the object then overcomes, or as the person overcomes the static friction, we then have a drop in friction, and it is now called kinetic friction. There's a drop there, you can see. It is constant. Kinetic friction is constant. And here we have our relationship. It is the same relationship. They are both directly proportional to the normal force, but we now have got a coefficient so that we can use this relationship to calculate things. And so kinetic friction is equal to the coefficient of kinetic friction times by the normal force. Whoa, that was a lot, grade 11s. In the next lesson, we're going to work through examples and see how we can apply our knowledge that we've gained today. I will see you next time.